The tech industry is hitting a strict physical limit. Global data center power consumption is rapidly approaching 100 gigawatts, driven by artificial intelligence compute demands. Terrestrial AI infrastructure is now severely bottlenecked. Expanding this compute capacity requires massive land acquisitions, grid expansions, and waiting years for new power plants to come online. The industrial response is already materializing. Elon Musk announced a $20 billion joint venture known as the TERAFAB at the Seaholm Power Plant in Austin. This facility will consolidate the chip manufacturing efforts of Tesla, SpaceX, and xAI under one roof, specifically designed to bypass these terrestrial power constraints. The TeraFab is slated to produce two distinct products. Alongside chips for autonomous vehicles, the facility will fabricate D3 chips, silicon explicitly tailored to survive and operate in the harsh environment of space. Musk's ultimate goal for the D3 chip is to power solar-driven AI satellites. By operating off-planet, the system aims to drop the raw cost of compute well below current terrestrial baselines. Tech industry capital is now pivoting to off-planet infrastructure, moving beyond software optimization to physically bypass the constraints of the terrestrial power grid. The architecture required to execute this mission already exists. Researchers at the University of Pennsylvania have published a rigorously modeled blueprint for a multi-megawatt, tether-based orbital data center powered entirely by the sun. The foundation of this system requires a dawn-dusk sun-synchronous orbit, or DDSS. This is a specific polar trajectory at an altitude of 1,600 kilometers that permanently rides the dividing line between day and night. Because the DDSS orbital plane naturally precesses, or slowly rotates, in tandem with Earth's annual motion around the sun, the satellite remains perfectly aligned with the terminator line year-round. The primary operational advantage of this specific orbit is constant energy. The system receives 100% continuous solar irradiance, meaning it never enters the Earth's shadow and experiences zero eclipse periods. Continuous sunlight completely eliminates the need for heavy, expensive battery storage. It also prevents the intense structural fatigue that normally occurs when spacecraft repeatedly heat up in the sun and freeze in the dark. By utilizing precise orbital mechanics, space transforms from a cold, hostile void into a constant energy environment, perfectly calibrated for 24/7 AI operations. The fundamental building block of this orbital megastructure is the individual compute node. Each node houses multiple CPUs and GPUs, graphics processing units, which are the specialized circuits required to accelerate the math behind AI. Operating this hardware in space introduces a severe thermodynamic problem. Without atmospheric air to carry away the heat, dissipating multi-kilowatt thermal waste from processors in a vacuum is incredibly difficult. The engineering solution relies on a closed-loop water cooling circuit. Small pumps pull the extreme heat directly off the chip's cold plates and circulate it out to large, lightweight external radiators. Water is chosen here for two specific reasons. It possesses excellent heat capacity, but crucially, when combined with an aluminum housing, the 20-millimeter layer of water acts as an incredibly dense shield against ionizing radiation. According to SpaceX, the Space Environment Information System used to model orbital hazards, a node at 1,600 kilometers will absorb roughly 10 gray of ionizing radiation per year. A gray is the standard unit for measuring absorbed radiation, and at this altitude, the dose is 1,000 times higher than on Earth's surface. Despite this intense exposure, recent terrestrial stress tests demonstrate that commercial tensor processing units, or TPUs, specialized hardware built purely for machine learning, can survive up to 150 gray of radiation without a hard physical failure. While background radiation will trigger intermittent soft errors and forced reboots, these millisecond interruptions are highly acceptable for AI inference tasks. Inference is the process of querying a pre-trained AI model, which operates in highly parallel, concurrent batches that easily route around a momentarily offline chip. The node's design elegantly turns a thermal necessity into a defensive asset, utilizing the liquid cooling medium itself as armor against the ambient space environment. Housing one node is solved, but stringing together thousands of these nodes to achieve data center scale creates a massive structural engineering challenge. If engineers used traditional rigid space trusses, the structure would quickly fail. Massive arrays buckle under their own compressive forces, requiring heavy structural reinforcements that completely destroy the economic viability of the launch payload. This schematic illustrates the University of Pennsylvania's alternative, a vertical, multi-kilometer tethered chain architecture. Instead of rigid metal, the array relies entirely on gravity gradient stabilization. This graph plots the opposing physics keeping the chain stable. Closer to the planet, Earth's gravity pulls the tether downward. Simultaneously, on the upper end, centrifugal force generated by the structure's orbital velocity constantly pulls the tether outward into space. This parabolic graph shows the result of those competing forces. The entire multi-kilometer tether is pulled taut, keeping it strictly in tension, with the maximum physical strain peaking precisely at the center of the array. Eliminating compressive buckling allows engineers to swap heavy metal trusses for ultra-lightweight carbon fiber tethers, a shift in mass that makes a multi-megawatt deployment economically and physically viable. While tension solves the static structure, the array faces a severe dynamic threat, impacts from MMOD, or micrometeoroids and orbital debris, which can strike the array and induce chaotic yaw spins. This flux chart displays the threat density at the 1,600 kilometer altitude, proving that high-velocity micro-impacts are mathematically inevitable over the multi-year lifespan of the data center. The conventional aerospace response is to equip every single satellite node with active chemical thrusters or heavy reaction wheels to counter the spin. But across a 1,000-node chain, the added mass makes that impossible. This diagram details a passive solution. The 3-meter PV panels are intentionally angled into a chevron configuration. When an impact causes a twist, the chevron geometry naturally alters the cross-sectional area exposed to incoming sunlight. This changing surface area creates an immediate imbalance in solar radiation pressure. The light itself pushes harder on the exposed side, generating a restoring torque that naturally forces the node back into perfect alignment. These dynamic response charts map out the results of this design. Combined with energy-absorbing viscoelastic tethers, this passive solar pressure reliably damps the angular momentum from impacts within hours. By angling the panels, the megastructure borrows momentum from light itself, achieving vital structural stabilization without consuming a single drop of active propellant. The final logistical hurdle is extracting the actual computational value out of orbit. Moving data from a 20-megawatt orbital computer back to users on Earth requires high-speed infrastructure. This is where the distinction between training and inference becomes critical. Training in AI requires impossible terabyte-per-second uplinks to feed massive datasets, but inference only requires preloading the static model weights once, and then transmitting low-bandwidth user queries up and down. To handle this traffic, optical router nodes are spaced at fixed intervals along the tether, aggregating the inference data generated by the compute nodes. These router nodes utilize targeted infrared laser links to fire the aggregated data across the vacuum of space, bridging the gap to existing relay networks. A 20-megawatt orbital center would require a maximum data downlink of roughly 10 terabits per second. Commercial constellations like Starlink already possess an aggregate network capacity exceeding 100 terabits per second. The orbital AI data center does not need to reinvent global communications. It simply acts as a massive, high-performance plug-in to a space broadband backbone that is already fully operational. Ultimately, the economics driving this architecture come down to the carbon footprint of compute. Launching a single compute node into orbit aboard a fully reusable next-generation rocket generates direct CO2 emissions. Getting a node to space costs 330 kilograms of carbon. Running it on Earth emits 8,000 kilograms of CO2 annually. Over 5 years, the terrestrial data center produces an order of magnitude more emissions than the rocket required for the orbital node. When that 5-year life cycle ends and the hardware becomes obsolete, the tethered chain uses solar sailing or its remaining thrusters to safely deorbit, burning up in the atmosphere to prevent orbital clutter. Driven by continuous solar energy and catalyzed by industrial deployments like Musk's TERAFAB, space is evolving. It is transitioning from a zone of passive observation into the next sustainable substrate for human computation.